In part 4 of our geometry explorations, we'll look at straight lines, and we'll start by going to the source. Our modern understanding of geometry goes back to Euclid's Elements, and so I want to point you at the first 6 books in English by John Casey from the 1800s. It's available from Project Gutenberg, which makes it an easy place for you to get a copy and take a look. Geometry begins with the point. In fact, it's definition 1. The point is defined to be something which has position, but no dimensions. In other words, this isn't a point, because a point has no dimensions. But we usually use a dot to represent a point, otherwise we couldn't see it. Remember the first postulate? We've talked about it a couple times. It says a straight line can be drawn connecting any 2 points. And we haven't really said much about what we mean by a straight line. And that brings us to definition 2. The line. A line is length without breadth. So this is a line also. Now we'd call this a curve. This is what the elements, at least the elements in English, would refer to as a straight line. We'd call it a line segment. So that's a straight line. Actually, that's a line. We haven't really said much about what straight means. So let's define straight. A line which lies evenly between its endpoints is a straight or right line, although evenly doesn't seem very clear. Another definition is a point that moves without changing directions describes a straight or a right line. So if we go back to our curve, you see we're headed in this direction as we go from left to right, and then at some point we're headed in this direction, so we've changed directions. In fact, we're constantly changing directions in this curve. Whereas in the straight line, we continue in the same direction throughout. So that's a point moving without changing directions. Henrique suggested that we visualize this by hanging a weight from a string, and that will straighten out the string. It will extend it and stretch it into a straight line. He knew this wasn't quite true because a string has dimension other than length. And so he said, abstract away from the string all of its thickness. This abstract idea is a straight line. Instead of abstracting away its thickness, I want to go the other way and fatten it up. And so for visualizing, I'm going to use masking tape. So here I've placed 2 coins on a table to represent points, and I'm going to use masking tape to represent a straight line between them. So why did I use masking tape? For instance, let's represent a curve. You may want to try this at home first. If you do, you'll see that the tape crinkles. You can see that here. Crinkles might not seem like a very technical term, but it doesn't differ that much from these definitions like lies evenly between its endpoints or moves without changing directions or abstract the string from all of its thickness. You can easily see the difference between these 2 lines. One isn't crinkly, one is, the straight line isn't. It's as if the line doesn't bend any more than it needs to stay on the surface and continue its path. So that's our idea of the tape crinkling. And for me, this embraces that feeling that geometry is just playing a game. We construct some rules and we play a game. And in our case, the game has been played on the plane using Euclid's rules. And Euclid's rules are just his definitions, axioms, and postulates. So let's leave the world where those rules apply. Picture a globe or a soccer ball, something round, something spherical. And let's do our geometry now on the surface of a sphere. And my question is, what does a straight line look like on the surface of a sphere? Let's start at any point and continue in the same direction. That was our definition from Euclid. Our way of intuiting it is to make sure the tape doesn't crinkle. So I've used a cantaloupe that's roughly spherical and some masking tape, and I keep stretching the tape and laying it on the cantaloupe carefully so that the tape doesn't crinkle. And when I'm done, I get this loop around the cantaloupe. It is a great circle. And this is a line on the surface of a sphere. This great circle is like we cut the sphere right through the center of the sphere. So now that we know what lines on the surface of a sphere look like, what about building parallel lines or triangles? We'll do all that next time.